Good afternoon. Okay, I'll have to restart this one. I don't know, it's not coming again. So the last day we were looking at the Navier-Stokes equations in a little bit more detail. So these are the Navier-Stokes equations for incompressible flow, conservation of mass, which becomes conservation of volume for an incompressible material, and it is conservation of momentum, mass by acceleration. Some of the surface forces, which are the viscous part and the pressure part, plus body forces here represented by gravity. So the last day I went through imagining a small piece of flow, a small region where there's a flow of material, and I just went through, well, how much fluid is flowing through this side of this little block, plus this side, plus this side, plus this side. And if the fluid is incompressible, then whatever flows in has to flow out. So we summed up what was flowing in at each side, but we said there's a certain velocity vector at each side, but only the normal component, the component that's perpendicular to the boundary, is actually bringing mass in or out. So if we sum up those normal components, and then we let this volume get smaller and smaller, the delta x and delta y go to 0. Then we found that we were able to express the sum of all the fluid flowing into a very small point can be written as the divergence of the velocity field. So for an incompressible fluid or an incompressible material, the divergence of the velocity field must be equal to 0. So if it's incompressible, then whatever flows in has to flow out. So this was how far we got last day. It doesn't work, still warming up. So I'm going to do a similar look into the conservation of linear momentum. So conservation of linear momentum. Okay, good. Conservation of linear momentum, as I said before, the left-hand side is mass by acceleration. And if you remember, this is this partial derivative term and this convective derivative, because we're trying to calculate the mass by acceleration of a moving piece of fluid, but we're not really tracking the fluid. We just want to look at what's passing through a particular region. So this is how we will correspondingly calculate the mass by acceleration of some fluid that happens to coincide with our box at a particular time. On the right hand side, we have the surface forces and the body forces. So let's look into each of these. So if we just look at the surface forces first, an incompressible Newtonian fluid, the forces on the side of this block, the surface forces, like we actually put a rigid block in here and the fluid is flowing over it, because of a non-zero viscosity, the thickness of the fluid will cause certain shearing on the surface, or some forces on the surface. So for example, like if you have something very thick like honey or ketchup, that obviously will maybe for the same velocity conditions would have a higher shearing or friction force on the surface. So that's what these viscous forces are. So if we have an inviscid fluid, that means the viscosity here is 0, in which case it doesn't exert any shearing forces. So there's viscous forces and then there's pressure forces. So if you have a certain pressure here and a certain pressure there, if there's a difference, that would be a net force due to differences in pressure. So these are the two key surface forces that appear in fluid flows. So these particular forms of expressions, where do they come from? So we can derive those in the same way we did for the divergence of velocity equals 0. So the divergence of velocity equals 0, that just came from, it's just summing everything, all the flow into a point, and that must be equal to 0 for an incompressible fluid. So that's what the divergence operator means. It normally means summing what's flowing into a point. So we'll do the same thing to see that this Laplacian operator and this gradient operator have a similar physical significance. So let's start with first looking at the pressure. So if we look at this same block in a flow field, and we have a pressure distribution as well. So there'll be some pressure at this side of this block, P1, some pressure at this side, P3, P2 at the top, P4, following the same number convention. So if I actually give you a concrete problem, I think I do actually have a question like this, maybe on the quiz or on the last year's exam, of just tell me what is the force due to the differences in pressure on this block. So if you have a certain pressure here and they're all pushing inwards, what's the actual force due to pressure, these pressure differences? The first thing to notice is force is a vector, so it's not a scalar answer. Due to these differences in pressure, you will get a force vector. You'll have a certain component in the x direction, certain component in the y direction. So you might just say, well, the force in the x direction is 4 times the area here minus 4 times the area there, if we're assuming positive in the x direction, so minus 0.5 meganewtons. And then the force in the y direction is 5 by this area minus 3.5 by this area, so 1.5. So the force due to these pressure differences in this case is a 2D vector minus 0.5 and then 1.5 in the y meganewtons. Okay, so that's how we do it for actual concrete numbers. So if we just do the same thing abstractly in terms of variables, we can see what the term ends up looking like. We look at one face and we look at the force due to the pressure on one face. We'll say, well, the force due to pressure on this face is the pressure at the face multiplied by the area vector, the vector area itself. So if we P1 here, P1 is a scalar, it's a pressure. And so if we multiply by this area, and not the magnitude of the area, but the actual area vector. So this face has a vector pointing in a certain direction. So it's the magnitude multiplied by the normal. That will give us a force. So in this case, it's minus because the area vector will be in the opposite direction here. So the force on any face is minus P times that area vector. So that's a vector force. So it's a scalar pressure, but it's applied in a certain direction. So that's a vector force. So following this approach that we did before, let's just sum up all those things over the 4 faces. So let's say the total force on this square is the sum from I equal to 1 to I equal to 4 over the force and the pressure force on face I. So we're just going to sum up the force on this face, this face, this face, this face. So if we calculate each of those things, we'll have P1 by the area vector here. And so this area vector, you can see the area of that face is delta y, that's the height of it, and it's 1d. So the delta y by 1, that's the area. And that's in the x direction. So delta y in the x direction, and this area vector has no component in the y direction. It's only fully in the x direction. So that means the force on this face here is P1 by delta y over 0. And the minus disappears because it was minus delta y, the area vector. So that's the force on that face. We can do the same thing on the top face. It has an area vector in the y direction of delta x. That's the area of delta x. P2. The same thing with this face, P3, and the area vector there is delta y in the x direction, and then P4 is in the y direction. So if we just bring the delta x and delta y terms together, we can say the force on this object is minus the difference between P3 and P1 by delta y is the height in the x direction, minus the difference between P2 and P4 pressures by delta x, which is the width of that face, and then that's applied in the y direction. So I just rearranged the terms on the last slide. So you can see this is the net force in the x direction vector, and this is net force in the y direction. So this makes sense from what we did before. It's just the difference in pressures here multiplied by the area, the difference in pressures here multiplied by the area. They're the two. So that's the force, but when we write our partial differential equations are per unit volume, so they're applied at a point. So these here represent forces per unit volume. So we're just going to divide by the volume of our element to get the force per unit volume. So divide by the volume of this, delta x, delta y, and then if it had a depth, we'll say it's 1. So divide by delta x, delta y. You'll see that instead of P3 minus P1 times delta y, it's now divided by delta x, because we're dividing by delta x, delta y, so delta y is cancelled. So the difference, pressure 3 and 1 divided by delta x, the width. That's multiplied in the x direction, and then the difference between pressure P2 and P4, and that's multiplied or divided by the y distance and applied in the y direction. So as we let delta x and delta y go to 0, then these differences become partial derivatives. So P3 minus P1 over delta x, that's as delta x goes to 0, that is just the definition of dp dx. So how pressure changes in x direction. Similarly, P2 minus P4, so P2 minus P4 over delta y, as we let delta y go to 0, that is just the definitions of dp. So you'll see that it's dp dx and multiplied in the x direction and dp dy in the y direction. So you can see this is just a vector minus dp dx in the x direction and dp dy in the y direction. So that is the force per unit volume at a point due to pressure differences. So I can separate out this del vector, this here, or it's called a differential operator. So d dx, d dy, I can separate that out. So you can see that this is a vector, d dx, d dy, just multiplied by the pressure. So d dx, d dy vector multiplied by the pressure, that gives you that. And then we can write this in with this notation, this del operator notation, as grad. So there's no dot, we call it grad, it's a cross without a curve. So minus grad. So like we did for mass conservation or volume conservation, now you can physically see that when you see this grad p term in conservation of momentum, and these are the sum of the surface forces, all this means is just getting the net forces due to pressure differences at a point. So if this is non-zero, that means that there's some pressure gradient, and that's like a net pressure force causing the fluid to flow. So if we want to get pressure fluid to flow in a pipe, we'll create a pressure difference. So if it's 0 at the outlet, we'll try to increase the pressure at the inlet with a pump or something, and that causes a net pressure difference. And that's basically just creating surface forces on all the pieces of fluid that cause it to drive in one direction. So for many incompressible flow problems, like aerodynamics problems, like for lower velocity, like cars and things like that, it might be this is the driving force term. I suppose the pressure forces are the dominant ones, and the viscous forces are more like secondary forces for less important. So if we were to go back to that problem and do the same thing, rather than calculating directly the force here and force there, the difference to get the net force, we could just do it as to calculate the gradient. So we get the gradient in the x direction for 4.5 minus 4 divided by the distance and 3.5 minus 5 divided by the distance. That's the gradient of pressure vector, and that is the force per unit volume. Actually, this unit is wrong. That's meganewtons. It should be meganewtons per meter cubed. I should fix that. Okay, so we had looked at this, and this peculiar term here just came from the definition of a partial total derivative. This is mass acceleration. We looked at this term here. This is the sum of the surface force. You saw where this comes from. So the only term we're missing in the Navier-Stokes equations for incompressible Newtonian fluid is this one. Gravity is simple. It's just adding the force at each point. So let's look at these viscous stresses. So the total viscous force on a region, like before, will just be the sum of the forces on each of the faces. So a little bit different from pressure. Pressure is a scalar, but in this case, the viscous forces are vectors. So if we go to any one face, we go to face 1, and there will be a stress due to the viscous forces that will have a component perpendicular to the face and parallel to the face. So we might call the perpendicular one, in this case, XX. So it's on the surface with the normal in the x direction, and it's applied in the x direction. So XY will be on a surface with a normal in the x direction, applied in the y direction, or positive. So it'll have an XX and an XY here, and then an XX and an XY there. So it's a vector. In 3D, it'll have an out of plane shear component as well. So this force here that's along the boundary, and that shear stress, if that was an actual wall, that would be called a wall shear stress. So often in fluid flow analysis, we're interested in wall shear stresses. So the wall shear stress is just this component, this viscous component along the wall. If you have an inviscid fluid, the wall shear stress by definition is always zero because there's no viscous forces. So for example, in biological flows, wall shear stresses, they know there's correlations between certain ranges of wall shear stresses and healthy flows versus if it's outside certain ranges, it might be pathological flows because the cells inside the arteries don't like certain wall shear stresses outside certain ranges. I think you can see where I'm going then. I'm just going to sum, in this case, the 4 vectors, and then I'm going to divide by the volume, and then let the delta x and delta y go to 0, and then see what the definition of the viscous forces become. And then you can guess that it's going to end up like this. So it's a bit more tedious because we have 2 components at each phase. And you can write it for 3D, it will be a bit more tedious. But let's just walk through it. We'll do the balance in the x direction and then in the y direction. So we will say that if we look at forces in the x direction, we have a T1xx here on that, and then plus the T3xx in that direction. So we have these 2 forces, and they're multiplied by delta y. So that's these ones here, multiplied by delta y. And then we'll also have the shear in the x direction here and here. So if we take this xx and this xx, and then this yx and this yx there, that's the net force in the x direction. So it'll be this one multiplied by the area, which is delta x, and this one by the area delta x, which is there. And then this T1xx and T3xx multiplied by delta y. So that's the 2 components, grouping them by the area in the x direction and area. So I'm skipping a few steps here. So I've already divided by the volume because rather than splitting it out, I'm just summarizing here. So I'm taking the net force, and now this is actually the net force per unit volume because I'm dividing by the volume. So you can see that's the net force in the x direction. Similarly, if I want to get the net force in the y direction, I can take 2 and 4 here. The normal components plus the shear components. So the normal components plus the shear components divided by 1. So then if we cancel out the delta y's and the delta x, the delta y's, the delta x and the delta y, and it'll end up looking like that. So you can see it's T3xx minus T1xx divided by delta x. So T1xx minus T3xx. Actually, the other way around, T3xx minus T1xx divided by delta x. And so you can see that this is the difference in the viscous stresses between this point and this point. So if we let delta x go to 0, that just becomes the gradient, the partial derivative, delta txx dx. So it's this thing here as x goes to 0 is just how the tau xx is changing in the x direction, its gradient. And similarly for all the other components, you can see this one, T2, Ty, yxx is just how tau yx is changing in the y direction, and similarly for the other components. So this is, once again, it's a vector force, it's the net force in the x and y direction. And this time it's written in terms of how tau is changing in the x direction and tau is changing in the y direction. So tau normally represents viscous stresses. That's just a term that people normally use in fluid flows. So sigma represents the full stress tensor, and so that would be viscous plus pressure. If you're only talking about viscous stresses, you normally just use tau. So it's the forces without the pressure part. So by definition, if we separated out the del dx and the del dy, you can show that this is the same as a second order tensor, the stress, the viscous stress tensor multiplied by this differential operator using a divergence. So that'd be a vector by a tensor, which gives you a vector for roll by column. So I've skipped over some steps here. But this, in the same way as before, you can see that the divergence of this tau tensor, this viscous stress tensor, is just the net force due to viscous stresses. So the divergence of the velocity was the net flow into a point, but the divergence of a tensor in this case represents a net force. So the divergence of this tensor equals the viscous stresses. Where does this thing come from? Well, for a Newtonian fluid, the viscous stress is the viscosity by the gradient of velocity. So that's the assumption for a Newtonian fluid. So if the viscous stress is equal to the viscosity by the gradient of velocity, and you sub that back in, then the divergence of that is divergence of tau. So tau is equal to the viscosity by the gradient of velocity, you get a divergence of viscosity by the gradient of velocity. And when you have a divergence of a gradient, that's just shorthand written as a grad squared, or it's called a Laplacian operator, or del squared operator. So that's what this thing is here. So this is viscosity, but this full equation has been divided across by density. So this is mu divided by rho. We call that kinematic viscosity. So when you see this term here, that is just the net surface forces due to viscous effects, and this is the net surface forces due to pressure. Any questions or comments? Thoughts? No, never. So I guess the goal here as well is to try to connect this to when you're using ANSYS, that you think a little bit about what's going on behind the scenes, that you're not just clicking buttons, you're actually thinking about what it's trying to conserve at each point and what the types of forces are and where they come from. So for the rest of this lecture, and then for the first one next week, I'm going to tell you a little bit about the finite volume method. So near the start of the course, we talked about finite element method. So the finite element method is using Abacus and these finite element softwares. And we talked a little bit from a physical perspective how that works and how these softwares are designed and written and what a stiffness matrix is and all these things and concerns related to that. So now I'm going to kind of do the same thing from a finite volume perspective. So the finite volume method is what Fluent uses. Fluent's not finite elements. This finite volume method, it's a related, it's a relative, I suppose, of the finite element method. So Fluent and OpenFOAM is used the finite volume method as well. But just to be clear that you can solve fluid problems using finite element, and you can solve solid problems using finite volume. It's just, this is historically the way these methods have developed. So if you use COMSOL as another software, COMSOL uses finite element for fluids and solids. But it's just finite volume is a bit more popular. So before I explain the finite volume method, it's useful to talk about another method called the finite difference method, and this is probably the grandfather of finite element and finite volume. They all came from this finite difference method. So it's useful to understand how that works, and then how the finite volume method is different, and then we'll also see how kind of that relates to the finite element method. So finite difference method is a predecessor of finite element and finite volume. I guess its origins are in the early 1900s. So let's just briefly review how that works. So to see how that works, I'm just going to take a simple PDE, partial differential equation, and show how the finite difference method would be used to discretize this or solve this on a simple structured grid like this. So this equation here, this Laplacian of phi equals 0. This is called the Laplace equation, or the steady state diffusion equation. And if this can represent lots of phenomena. So phi here, that's temperature. This would be the steady state heat equation, like you would have looked at in algebras. So this is a very simple equation to solve. So it'll show you how it works. So this could represent the sum of the heat fluxes into a point, and saying they're equal to 0. So let's see, how do we discretize this on a structured grid? So maybe it's easier if we just write out this in component form. So let's imagine we have a 2D grid. So actually what this is saying is the second derivative in the x direction of this phi, which could represent temperature, and plus the second derivative in the y direction of this phi temperature is equal to 0. So if we sum those second derivatives, they're equal to 0. That's what this equation says. So this also could represent like the viscous term. So The viscous term is viscosity by the blasting of velocity. Velocity is a vector, but if we take just the x component of it, this is like a similar form to what that term looks like. So if we take this partial differential equation, that's an equation defined at a point. So we're not talking about something integrated over any volume or anything, just directly at a point. We know that this equation should hold at every point inside our domain. But what the finite difference method does is it doesn't try and force it at every point in the domain. It just picks certain points called the nodes, and it just says, let's just enforce it at each of these nodes. So let's use this compass notation. We'll say P is the node we're trying to write this equation at, and then north, south, east, west. So how can we write this partial differential equation, this continuous equation, in terms of phi's, the values of phi at these nodal positions? So to do that, we basically just have to figure out, well, how can we calculate this or approximate this second derivative in the x direction and second derivative in the y direction at point P, using the values of phi at the surrounding nodes. And there's a few different finite different ways to do this. I'll show you maybe a classic, simplest way. So let's just do the x direction. If we can figure out the x direction, we can just do the same thing in the y direction. Okay, so instead of dealing directly with the second derivative, let's just split that as it's the derivative of the first derivative. So the first approximation we're going to say is, okay, so we're just trying to get a derivative in the x direction, like how much something's changing at point P in the x direction of this thing, which is the first derivative. So if we were to get the value of this first derivative at a point PE, so that's a point halfway between P and E. If we did know the derivative at that point, and we knew the derivative d phi dx at WP, in between WP, if we knew the derivative there and there, then we can say, well, that's this second derivative is approximately equal to the value there minus the value there divided by the distance. So that's like the essence of the finite difference method. It's called a finite difference because it's a difference across a finite net. So by this is an approximation here. This is where we're introducing a mesh error, an interpolation error. We're essentially assuming like a linear variation at this point. So that's introducing an error that's proportional to this delta x. So we have to do a mesh sensitivity study the same way to find out why. Okay, but we're not done because we want to write this whole term in terms of the values of phi at the nodes. So at the moment, we've just written in terms of the value of the gradient of phi at the center of these edges. So then if we look at the gradient of phi at PE, this grad phi at PE, this term here, we can also add a second approximation. We can say that that's just equal to the value of phi at E minus the value of phi at P divided by that distance. So I'm assuming the mesh spacing is delta x in its uniform. So now we've written this term in terms of phi's at nodes, just two nodes. And similarly, for this point here, we can write d phi dx at WP as phi p minus phi w divided by that distance. If we substitute those two definitions, grad x at PE and WP, back into this term here, then that completes it. That lets us write the derivative, the second derivative at point P. So substitute those in, this one to here, this one to there. We have delta x is here, phi p appears in the both terms, but phi east only appears in the left and phi west only in the right. And you can see there's a minus and a minus. So if we just rearrange that, you'll find that it's equal to that. So this d phi, this second derivative of phi in the x direction, you can say with two levels of interpolation approximation, it's approximately equal to the value phi e east plus phi west minus 2 times the value in the center, phi p divided by the delta x squared. So even though it's not shown here, this is a second order approximation. So as we refine the mesh, we'd expect the error to reduce at the rate of delta x squared. So you can do the same thing in the y direction. So if that's in the x direction, if you do the y direction, instead of phi east, you'll have phi north, and then you'll have phi south instead of phi west. But phi p appears again. So you can see phi p, there's two here, and there's a delta y. So our final equation was just adding both of these together, the scalar equation. So if we add both of those together at point P, this, and the conservation equation says that the sum of both those things should be equal to 0. Or at least this is an approximation of that, it should be equal to 0. So sometimes people then will rearrange it. They'll say, well, rearrange the unknowns here are the phi's at the nodes. Do you want to solve that? We want to calculate those. So we could form this type of equation for every node in the mesh. If we use 1,000 of them, we could form the same equation for 1,000 of them, incorporating boundary conditions, anything we know at the boundary. Then we'll have 1,000 equations with 1,000 unknowns in terms of 1,000 unknowns. So sometimes people will separate it out into what's multiplied by the unknowns. So you can see we have 1 over delta x squared, or multiplied by the unknowns at east and west, 1 over delta y squared for the unknowns at north and south, and then we have 2 over delta x squared plus delta y squared. So if you were solving this in an implicit method, these are the coefficients that go into the matrix, like essentially like the stiffness matrix for the finite difference. So we can apply it after all n nodes, we get n linear simplex equations, and we can solve for phi's at nodes, and then if you know the value of phi at boundary, then you would just incorporate that number directly in, like we do with the finite method, or maybe you know efflux or something like that. So that's the finite difference method. There's some similarities you can see with the finite element method, but there's no definition of an element, and there's no integration over an element. It's just at nodal values you're trying to enforce it. So whereas the finite element method might be enforcing it over in an integral fashion over the elements themselves, that's not the case in finite difference. It's just at each node you're trying to enforce the equation. Okay, so that's the finite difference method. Sorry. So 60s, 70s, 80s, even into the 90s, finite difference method was particularly popular for fluid mechanics. Just finite difference method like that was used for fluid mechanics. And if you look up some books, there's an Anderson Computational Fluid Dynamics book, which is popular, and that only uses the finite difference method. But extending the finite difference method to unstructured grids, and we talked about structured versus unstructured grids. Unstructured grids, in an unstructured grid, you don't necessarily have north, south, east, west. You might have a bunch of elements around you. So the finite volume was an extension of the finite difference method to account for unstructured grids and more complex geometry. So the finite volume method is a generalization of the finite difference method, but a very different philosophy is adopted. So while the finite difference method takes this differential equation and tries to enforce it at the points, the nodal points, as we'll see, the finite volume method is going to use an integral form and try balance forces on these individual cells or volumes. That's the kind of key philosophical difference. So for finite volume, we're going to start with this form of the same equation. So you can switch between the two of them. So if we did have this equation, if I just integrate this over some finite volume, some region of space, like a cell, and maybe here's the volume, and just integrate it over the volume, that also should equal to 0. So if this thing is equal to 0 at every point, if I sum over a bunch of points, that also would be equal to 0. If I wanted to go back, I just let this volume go to 0, and then I can get back. So this is called the differential form, this is called the integral form. So finite volume, we're going to start from this integral form. And when we have a divergence of a gradient, the Laplacian is the same as a divergence of a gradient, we can use this Gauss Green formula to switch this. There's no approximation, it's just a mathematical equivalence or identity. You can switch this to a surface integral. So gamma here is a surface. The circle means it's a closed integral. So if I integrate this thing over some volume, that's equivalent to integrating n dot grad phi over the surface, that closed surface of that volume. So the finite volume method enforces this integral form of the equation over each cell. So normally they call it a control volume, sometimes a control mass, depending on what you're talking about. But essentially it's a cell, it's an element. It's the same as like a finite element method. A key distinction in so-called cell-centered finite volume methods, if we compare to finite element, is we're going to calculate values at the centers of the cells rather than at the vertices. But you can actually have vertex-centered finite volume methods. But Fluid uses a cell-centered method like this. So the primary unknowns, what we're solving for, the phi's will be phi's at the centers of these cells. So then the question is, how do we write this thing over this volume here? So if you integrate this n dot grad phi over the surface, the four flat surfaces, that equals 0, and write that in terms of the values of phi at the nodes in this so-called stenciler or molecule. How do we do that? This integral here, n dot n is the outward pointing normal unit normal, dot grad phi, so that represents a gradient in each direction of this phi. We want to add that or integrate that on the surface, this blue dashed line. First thing we're going to do, no approximation, just mathematical splitting. We have a closed integral over this surface. We can just split that into a sum of an open integral here, here, here. We'll just say this is a sum over the four faces, or how many faces we have, of open integrals. So F being representing the face, so east, north, south, west. North, west. But that's just an equals. I haven't made any approximation or made any assumption about the variation. So here's the first approximation made in the finite volume method. For each one of these spaces, we have to get n dot grad phi at that face. So you can integrate that over the face. In reality, this might be varying along the face. The value here might be different from the value there to the value there. It might be depending how coarse your mesh is and the physics going involved. It could be a very complex polynomial or something more exotic. So the first approximation we're going to do is we're going to assume a linear variation. So phi, we're going to assume it varies linearly across the face, like a linear interpolation function or shape function finite element. Let's assume it's linear. If it's linear, then we can use what's known as the midpoint rule. So if this thing varies linearly, we can use the midpoint rule, which says that for a linear variation, we can exactly calculate it by just taking the value at the center of the face. So in this case, this represents, if we calculate this n dot grad phi at the center of the face, just multiply by the area vector, and that would be that's consistent with a linear variation. So this closed integral has four terms. So if I just write that out for the four terms, so east, north, west, south, we'll have east, west, north, south. So this n dot grad phi, we haven't talked about what that is. This gamma is just the magnitude of the area vector. So just like the area, the scalar area. So we just have a sum of four terms. So that's approximately true. This approximation here, midpoint rule, as I said, is consistent with like linear shape functions. And then there's a second level approximation, just like in finite difference, we have these two levels of approximation. There's a second approximation where we will try to calculate this n dot grad phi at a face. So how do we do that? So n dot grad phi at a face. So if you write out this grad phi, that will be d phi dx, d phi dy, the vector. And then n dotted will be the component of that vector in the direction of n. So if we are at the face where n is equal to 1, 0, so 1, 0 by this grad phi x, grad phi y, we'll just take the x component. So this is a scalar and this is a vector. So at the x face, this thing is just d phi dx. So if we can just calculate d phi this dx at the center of that face, then we're done. And then we will equally do the same thing at north, west, south. So d phi dx, like the finite difference method, we can just say, well, that's approximately equal to phi east minus phi t divided by delta x distance. And that's consistent with assuming a linear variation. So that assumption of a linear variation there and in the previous slide, they can be replaced with quadratic or cubic or something else, and that gets so-called higher order methods. They're less common in finite volume, but they can be done in the same way that we could assume a more exotic interpolation function in finite element method as well. So then we will do that for the other face as well. So west, north, south, in terms of the two values of the cell centers. Sometimes, even though nodes can mean corners in finite volume, when they talk about the nodes, they just mean where the variables are stored. So the nodes here will be at the cell centers, the computational nodes would. Then the final discretized governing equation for the finite volume version of this diffusion equation. We'll take this one. So we can multiply by the area vector. So these gradients by the area vector. So like this, the area vector here is delta y, and this is delta x. So you get something that looks like this. And then that gives you the net force or net heat flux in that cell. So the finite volume method is giving you the absolute value of like heat flux or force, whereas the finite difference, because it's the differential form, it's per unit volume. So if we wanted to compare them, we could just divide this by the volume of this cell, and that would be per unit volume, and lets us compare exactly the finite difference, the finite volume. So actually, in this case, if we divide by delta x, delta y, we'll find that for this type of grid, the finite difference and finite volume method are identical under these assumptions. You get the exact same value, the exact same equation. So that's not true for more complex cells, but for this very simple mesh, that is the case. So we divide across by that, and we'll get something that looks like this with delta x squared, delta y squared. So if you remember the past equation for finite difference, I think this is the finite difference one. Yeah, this is the finite difference one. It's exactly the same. Like the terms are identical under the same linear interpolation assumptions. But if we have an unstructured mesh, the finite difference method can't be applied to that so easily, whereas the finite volume method, you can, because it's just summing up the faces and it doesn't say how many faces you're limited to. Then just to end on this slide, if I design on purpose a grid that looked like this, where we have triangles, we have the center node, and we have the triangles that look like this. And then we use the finite element method where our triangular formulation, but instead of the structural displacements, we just did it in terms of temperature. So one temperature at each one, or one phi. If you were to use our linear shape functions, you'll find it's actually identical as well. So for this simple type of structured grid, finite difference, finite volume, finite element actually all give the exact same formulation. But in general, they don't. It's just to show that they do coincide at some points. This is a good place to stop. Thank you very much. Any questions, you can just come up to me afterwards, or any questions about the labs tomorrow, you can drop up to me, and some people maybe have sent me emails, so I'll try to get to those, but you can come up and ask me now as well. Yeah.